People are missing. I wonder if people are getting sick or something like that. Something coming up next week. Something weird happening next week. Allergy season, definitely.
Yeah, next week.
I think it's just springing into everyone's system. They really need a break. So, anyways, so yeah, please remember that next week is spring break. You can come to campus if you want, but I won't be here. Not many people will be. Not many things around the campus will be in operation. So you don't need to come to campus that next week. Have a great, definitely well-deserved time off, and then come back refreshed and ready to go after that. We have our next exam is in week 11. So we get back, we have week 9, then week 10, and then we take week 11. So we got a little bit of time before the next exam. We left off last time talking about the Pythagorean identities. And so fun fact, what I'm going to do, I finally thought about it and I decided I am going to make you on the first page of the exam. There is going to be this, and you're going to have to deduce all of them so that you can use it on the exam. You can keep that page. Maybe it'll be on the back page so you can rip it off and then I can staple it back together or something like that. But you'll have it there for reference. So you don't have to have them memorized. You can deduce them and then they're all there for you. And that's worth credit on the exam. So that's kudos. Thanks, Phil. I really appreciate that. Absolutely. You're welcome, Therese. I appreciate you mentioning that you appreciate it. Okay. So anyways, back to the point. Yeah.
You said that you only remember the first one and then you derive the next two and then you work down. Obviously, working down is the easy part. But what's your method for developing the second two?
So it doesn't matter which one you do first, but you know that you have to divide by sine squared or cosine squared. And then to get to this one, you have to divide by cosine squared. Because then you'll get sine squared divided by cosine squared. That gets you the tangent. Cosine squared divided by cosine squared. That gets you the 1. And then 1 divided by cosine squared. That gives you the secant squared.
Oh, so either one is, you're just dividing by, so the first one is cosine.
Yeah. The first one you divide by cosine squared. The second one you divide by sine squared. But I'm not going to make it something where you have to write them in a specific order. Just know that you have to divide by one of the 2 main trig functions squared.
Then the second, you're just divided by sine squared.
That's correct.
How do you know what you have to divide by?
So it's just sine or cosine, because there's only one way to get a tangent. That's sine over cosine. There's only one way to get a cotangent. That's a cosine over a sine. So that's why you have to divide by those ones. At the end of the day, every trig function can be written in terms of sines and cosines. So, all right. So now we're going to be trying to do some extra stuff. We're going to be trying to simplify some identities. We have cosine squared x minus sine squared x cosine squared x. So what we do? Plug out, factor out the cosine squared. So this will be cosine squared of x times 1 minus sine squared of x. And that's just algebra. So I noticed that there's a common factor of cosine squared x. So that's algebra. I didn't do any trig. I just did algebra. I did factoring, which is algebra. Then, as soon as I see a 1 minus or a 1 plus something squared, I immediately think to my Pythagorean identities. So what is 1 minus sine squared of x equal to? Cosine squared x. And you can look at this. If you do it enough, you start to memorize it. Like you start to recognize what it's going to be. But either way, that's going to be equal to cosine squared. So this equals cosine to the 4th of x. And that's going to be by a Pythag identity. You're not pleased.
I just didn't realize. In my head, it seemed like it had to be 2 cosine 2x. But I guess that works out the same.
It should so it's gonna be cosine squared times cosine squared. So the exponents add together. Yeah. Now we're gonna learn about half angle and double angle formulas, and there is a way to break that down into some interesting stuff, but we don't need to worry about that right now.
Is a test question with 2 cosine squared X be
Incorrect. Yes. If it like, so that's the difference between cosine squared of x plus cosine squared of x. That is 2 cosine squared of x. But cosine squared times cosine squared is cosine to the fourth. All right, the next one, 1 plus cotangent squared times sine squared. A couple things could be possible here. One thing you could do, so there's many different myriads of options. The simplest way, the fastest way, in my opinion, is to notice that this is a Pythagorean identity. 1 plus cotangent squared, we can look back up here. 1 plus cotangent squared is cosecant squared. So that would be what I would do. This is cosecant squared of x. So this is equal to cosecant squared of x times sine squared of x. And that's by a Pythag identity. Then the answer should be 1. Because cosecant squared, that is 1 over sine squared of x. And so those are going to cancel. I guess I need to write this down in 2 steps. Like depending on how you have to do it in ALEKS, they might say that you need to use the reciprocal identity. So I guess technically speaking, what I should do instead of writing it like that, I should say that this is equal to 1 over sine squared of x times sine squared of x. And that's by a reciprocal identity. And that's the way ALEKS wants you to write it. I don't care about you writing the terminology. You can just say 1 over sine squared times sine squared and cancel it out. That's fine with me. I'd encourage that. You don't need to say what it is, in my opinion. Jake, do you have a question? And then they cancel, and that's algebra. So then these cancel, and that's going to equal 1, and that's algebra. Any questions on that? However, there is another option. And I'm gonna go ahead and do it just in case you want to see it. So it was once again alternative. So it is 1 plus cotangent squared of x times sine squared of x. If you don't remember the Pythagorean identity, one thing I know about cotangent is cotangent is cosine over sine. So I could rewrite this as 1 plus cosine squared of x over sine squared of x times sine squared of x. Remember, if all else fails, if you're feeling overwhelmed with it, try and convert it to sines and cosines. It might work, it might not. But at the end of the day, it may be like it's worth a shot. No, some work is better than no work at all, right? And then, so that's going to be reciprocal identity, or do we call it reciprocal or quotient identity? Stupid, but either way, quotient identity. And then I'll do some algebra. I'll FOIL or I'll distribute this in, and I get sine squared of x plus cosine squared of x. And that's going to be algebra. And then last but not least, sine squared plus cosine squared is equal to 1. That's a Pythagorean identity. So that's the key thing, is that there are multiple ways to go about this. And I will be like, I have to painstakingly go through these if and when these do show up on the exam. I will have to make sure that all of your work is right because there are many avenues that can be approached to get this stuff done. Any questions on that? Okay. So that's just an alternate route. Oh, sure. Yeah, the tangent and cotangent being sine over cosine and cosine over sine. That is what we call a quotient identity. I don't need you to write that on the exam. You can just write it as cosine over sine, and we'll call it good, or sine over cosine.
What did you do with the sign? Did you distribute it?
Yes, and that's algebra. It's just simplification. Right? So now we can go on to actually verifying trigonometric identities. So we're going to say the rules, which is one way to do it. I prefer like just starting with one side and deducing the other. That seems more natural than just saying a bunch of rules, but either way. So we're going to complete the proofs of the identities by identifying the rule that justifies each step. Your choices are algebra, reciprocal, quotient, or Pythagorean. So sine squared minus sine to the fourth x. That's just the statements. That's the starting point. So NA, left-hand side. However you want to write it. There is no rule happening there. We're just starting with the left-hand side. There's nothing stopping us from starting with the right-hand side. We could definitely do that. When you're proving that identity, it's an equal sign. So it's true backwards and forwards. So you can start with the left-hand side, start with the right-hand side. It's your call. The first step that is given by the person, whoever this is that they factor out a sine squared x times from it and get sine squared x times 1 minus sine squared of x. What is that? Is that algebra or an identity? It's just algebra. We're factoring. Because factoring. Because we're just factoring out, it's algebra. You don't need to write the because factoring out. You just write algebra, but the reason why it's algebra is because we're factoring. All right. Then it says that we're going to change from sine squared times 1 minus sine squared to 1 minus cosine squared times cosine squared. That's a little bit of a cheap shot in my opinion. That's actually 2 steps in one, but because they're both the same type of thing, they're letting it be done in one step. Yes.
Which step are we on?
We're on step 3. No, go ahead.
Can you just repeat what you said? Because I didn't see it. I thought you were talking about, it looks like it's just a factoring to me, but.
So from here to here is what I'm talking about.
Oh, I see.
So this is this is 2 steps in one. I don't think it should be written this way. I think it should be written in 2 steps, but this sine squared is being converted to a 1 minus cosine squared by a Pythagorean identity. There's
They're not just on the right side right now.
Nope, they're trying to deduce the right-hand side. Is that okay? We're trying to get what we started with to the right-hand side. It's okay if that's not okay, though.
It's not getting off.
All right, I appreciate it. The other one, this thing right here, 1 minus sine squared of x, you can rewrite that as cosine squared. So, by the way, in case you're curious about what's going on here, this is something you might see on Alex. It's going to give you the steps of the proof that they've decided upon. So this is not me writing this. This is an Alex problem that's saying this is what's happening. It's trying to help you identify what rules that you need to use. But at the end of the day, we're going to be more interested in doing it ourselves. We're going to be choosing the rules that we're going to use. So that's where we come into play. But this is just trying to get us comfortable with notation and stuff.
I looked at the previous step was actually an operation done on the right-hand side of the equal sign. Right?
It's like you're taking the left-hand side and you're factoring it out. So really, it's a string of equalities. So what it should look like, going back up here for a second, the way you would prove it written down, it would be sine squared x minus sine to the fourth x is equal to sine squared of x times 1 minus sine squared of x. Is there a question? No, we're good? Okay. No, Eli and Catherine, are we okay? So I hate to be this person, but you guys are talking and it's might be distracting the people around you. Okay. And then what I would do is I would change the sine squared to a 1 minus cosine squared. And then I would change the 1 minus sine squared to a cosine squared. So this would become 1 minus cosine squared of x times cosine squared of x. And then I distribute, which will then give me cosine squared of x minus cosine the fourth of x, which is what we wanted to show. So it's just a string of equalities. So we're starting with the left-hand side, working on it, and bringing it down to make sure it's equal to the right-hand side. No, it's fine. Like it's a weird situation, right?
I don't understand. For example, cosine squared of x is equal to 1 minus sine.
That's one of our Pythagorean identities up top. So remember that, like from last time.
Different versions?
Yes.
Okay.
Everything can be deduced. All other 8 identities can be deduced from just this one. And for like, a couple of people did come in late, so just letting you know, the first page on the exam, or either the first or the last, will be for credit, and it will be deducing all 9 of these. So you can deduce them all. Maybe I'll even write the sine one, the secant one, and the cosecant one, something like that. But either way, you can deduce them all just by dividing by sine squareds or dividing by cosine squareds. But yeah, that's what we're using there. So the sine squared becomes 1 minus cosine squared, and the 1 minus sine squared becomes cosine squared. Those are both Pythagorean identities. I wouldn't put them in the same step, but that's what the ALEKS program did. So this is going to be Pythag. It's a Pythagorean identity. And last but not least, you come to your final answer because you are foiling, or not foiling, you're distributing. So algebra, yes. Any questions on that? Otherwise, we can do the next one. So,
To be clear, all we're doing it because we're breaking down all of the steps that it took to make the right side look like the left side.
that is correct. We are trying to show that the identity works and showing all the individual steps that were needed to show it. Next one, tangent times cosecant squared minus 1 is equal to cotangent. So there is no rule on the first side. That's just the left-hand side. You don't really need to write anything there. Honestly, I would just say NA. There is nothing happening there. So whoever wrote this proof decided to change it from that to sine of x over cosine of x times cosecant squared minus 1. So what do? Quotient rule. They use the quotient identity on tangent to convert it to a sine over cosine. So the tangent becomes sine of x over cosine of x. That's going to be a quotient identity. The next thing that changes is the cosecant squared minus 1. That changes to a cotangent squared by one of the identities up above. In particular, it's a Pythagorean identity. And if you don't have highlighters, you can always underline things with squiggly lines or tornado lines, you know. My favorite type of underline is a tornado. Those are fun. But you can do a squiggly line, just you can color code without color. Then what happens is they change cotangent squared to cosine squared over sine squared. So that's going to be another quotient identity. Then all of that stuff gets slightly canceled. Yep, algebra. And last but not yes, and Lamar's absolutely right. Quotient's the last thing. This we haven't used red. Let's use red. Now sine or cosine over sine gets converted to cotangent, and that's a quotient rule. That's a quotient identity. I get why they do this, but I prefer just to work with it. I prefer it. And I feel like that's going to make it look a lot better for us. So any questions on that? So it's just identifying, like this type of problem is just identifying what step is happening. But now we can actually do it ourselves. So we have all of those identities up there. And remember, you're going to deduce them on the exam, so you don't actually need to have them memorized. So it's basically, you're going to be making this, the Pythagorean identities on your first page. These ones, I hope that we almost have these memorized at this point. We use them so often. Yes.
So if you mess up your table.
Ooh, good point. Good point. Good point. Best not mess it up then, right? Be good with your algebra. Remember, I think I said this class that I said in this class about calculus was the hardest part of calculus, the algebra. So being good at algebra is very important. But so once again, I'm not going to provide the reciprocal identities. These things are so core to trigonometry. You just need to know them. You just need to know them. You've used them so many times at this point, and you will continue to use them so many times that they just become second nature. So we're going to start proving these types of things. Cosine times 1 minus tangent squared x is equal to secant of x. And my recommendation is to watch Pirate Radio if you haven't seen that movie. It's a great movie with starring Philip Seymour Hoffman. It's a great movie. It's very, very enjoyable. That's not actually a recommendation. I'm suggesting start start with the more complicated side. And try / pray. Usually speaking, the more complicated side is the one that has more things that can be broken down into pieces. So it's much easier to break things down than to build them up from scratch, right? If you give me a built-up Lego set, it's much easier to break it down into pieces than it is to try and create the Lego set without any of the information given, right? Trying to create the dragon or the little semi truck that that I got my son tonight this morning. Trying to break it down is much easier than trying to build it up with no instructions. So it's best to start with the more complicated side because there's so much more you can do with it. And if it doesn't work out, if you're stumped, erase it all, try again. Try with the other side, see what happens. And if the other side isn't helping you out, go back to the left-hand side again and try again. If at first you don't succeed, try again. So you're always going to start with the left hand. You're always, like, my opinion, you start with the more complicated side, which in this case would be the left. So I'll start with the cosine. I'm even going to write this. more complicated. So I'll start with that side. Cosine of x times 1 plus tangent squared of x. And remember, there is no one right answer. One option you could do would be to write the tangent in terms of sines and cosines. That is an option. You can do the quotient option. The easier option, the more apparent option would be to use a Pythagorean identity. So this, right, let's use green. Looking at my Pythagorean identities that I've deduced myself, 1 plus tangent squared, that's secant squared. So this equals cosine of x times secant squared of x. And that was by a Pythagorean identity. Now what should I do? The reciprocal identities. Secant is relatable to cosine. Every x gets a c. So this could be rewritten as cosine of x times 1 over cosine squared of x. And that's a reciprocal identity. Yes, it will cancel one of them. So now this cosine cancels one of them. And we're left with 1 over cosine of x. And so that was that an identity at all? Nope, it was just algebra. Just algebra. All we did was we canceled common factors. That's an algebra thing. And then the final answer, keep in mind, we always want to get back to the right-hand side. If we start with the left, we want to get to the right. If we start with the right, we want to get to the left.
We can start with the right.
Mm-hmm. Absolutely.
The second one.
Mm-hmm. Yeah, you could do that. Totally fine to do so. And so last step is that this is equal to secant of x, which is exactly what we want. And that's a reciprocal identity again. On an exam, as I said, but I'm gonna say it again, you don't need to write the identity being used. You don't have to do that. You can just use your knowledge to simplify it. I would honestly, so on an exam, I'd be fine with you going from here to the end, because like that's 1 over cosine. We know that that's secant. Remember, I'm trying to make sure the idea is that you should show enough work that a classmate could understand. And we've all practiced using the reciprocal and quotient identity so much. We know what 1 over cosine is. So why rewrite it? You know that this is 1 over cosine, so that equals secant. You can do that. That's fine with me. Just remember to try and appeal to the average student in your class. So like if you think that it wouldn't make sense unless you included the step, include the step. And so then we get to put a big check mark or a black box or a QED, whatever you want to do. Any questions on that? I do want to show you, though, you could have done it differently. So you can add this to your notes if you'd like. I'm just going to show you, might as well, because like looking at how much work do we have left? We have that one, that one, that one, and that one, that one. So that's all we have, and we have plenty of time. So might as well show you this one. So this would be an alternative for A. You don't have to write this down. You can just observe because it's not required. But I just wanted to show you you can think outside the box. So I'm going to start with the left-hand side once again, cosine times 1 plus tangent squared of x. And I'm not going to write the identities that I'm using now. So, oh, not cosine of, that should be cosine of x. Dope. That'll be cosine of x times 1 plus sine squared of x over cosine squared of x. Oh, no, it's not. It's going to be funny. It's going to be fun. All right. So you can get there in a myriad of ways. This one, it's not going to be as intuitive, I'm letting you know, but it's good to practice the thing outside the box. So if I'm truly lost and I can't remember my identities, try and convert things to sines and cosines. Then I'll try and do, so this is a quotient identity, and then I will distribute. That gives me cosine of x plus sine squared of x over cosine of x. That's just some algebra, right? Okay. What do I do? There's plenty of things I could do. Marcus, yeah.
You add them.
That is the perfect idea, but you need, sorry, what did you say?
If you just put the cosine on each denominator by multiplying the top and bottom.
Exactly right. As soon as I see fractions, I think maybe I should try and combine them. Another option could be to rewrite sine squared as 1 minus cosine squared and see what happens. That also will work.
We used to dividing and distributing them with numbers, not with cosine and sine, like,
Mhm.
so like you just made listen to cosine, right? You just took out cosine of the square to x and then just subtracted one, right? Didn't you?
Mhm.
That's all you did?
So I distributed the cosine into the first one. That's where I got the cosine of x. And then when I did it to the second one, it canceled one of the cosines.
But it doesn't affect the sine of two, right?
Nope. Because that's the same cosine of x is the same thing as cosine of x over 1. So you can cancel diagonally. All right.
I guess you're going with numbers like
I get you. So there are two avenues we could go down, and both will get us there. Marcus, that was the way I thought of doing it, would be to find a common denominator. So multiply this by cosine of x over cosine of x, because it doesn't have the same denominator. It's missing the common denominator of cosine of x. So I multiply it by what it's missing, which in this case is just cosine of x. That gives me, now by multiplying by in purple, I have guaranteed they have the same denominator. So this now becomes cosine squared of x plus sine squared of x over cosine of x. And that's just algebra. So far we've done algebra, we did a quotient identity, then algebra, and then algebra again. But we know what cosine squared plus sine squared is. That's 1. So this is 1 over cosine of x. That's a Pythagorean identity. And then the reciprocal identity equals secant of x. So there's another way to do it. And a third way, I encourage you this week, this spring break, if you're bored and you're trying to figure out something to do, because I know we don't have anything to do during spring break. We don't want to do anything fun during that time period. We could definitely spend some time with our friends doing this type of stuff. Try and prove it by turning this into a 1 minus cosine squared. I guarantee you'll get the same answer. Brian.
Cosine. If you were to make the cosine squared of x to just cancel out with the bottom, so it'd be cosine of x plus sine squared of x.
That like that? Is that what you're saying?
Yes.
Ah,
I didn't see
the 1 plus the yeah. So
I see the up there, but if I was to do that, would I get the answer?
well, Brian, you'd break my heart. You would break my heart if you did that, because that's not real algebra. We can cancel factors, cannot cancel terms. So if this was cosine squared times, if this was times here, then they can cancel. But just like if you have 1 plus 3 over 9, we don't get to do that, because 3 is a factor in the denominator, but it's a term in the numerator. And you can't cancel terms with factors. You can only cancel factors with factors, and you can only cancel terms with terms. Is that okay? So, yeah. Don't do that. Don't do that. It breaks my heart. So, All right. Now, as Eli suggested, you can start with the right-hand side of this one. Let's do that. Let's find what happens. I don't know what's going to happen. I'll start with it, see what happens. For giggles, let's start with right-hand side. Sine of x times tangent of x. Okay. Let's see what happens. Quotient rule, yes. We'll change the tangent to sines and cosines. If all else fails, convert things to sines and cosines. This becomes sine of x times sine of x over cosine of x. Now what? Well, then algebra would suggest, and you could probably even skip this step and write this as sine squared of x over cosine of x. I would be fine with that. If you wanted to go straight from here to here, I'd be totally fine with that. And that's just algebra. If I really wanted to go through all the nitty-gritty details, yes, then you have to first say it's a quotient rule, then it's some algebra. Now what? 1 minus cosine squared, a Pythagorean identity. Remember your Pythagorean identities. Keep it handy. I think the way I'm going to try and do it is make sure that the question, let's be honest. Let's be real with each other. You know, there's going to be at least one question like this on an exam, right? It's just a fact. This is one of the sections we're going over, so of course there's going to be something on here. That's just a fact. So I'm not really revealing anything like, oh, my teacher told me what's on the exam. No, I'm just telling you what like it is, like a student would think. And so I promise you, if that happens, I'll make sure that the questions that have identities are right next to the ones that have the identities, so you can keep the exam open with both pages, so you can reference it. Does that make sense? But yes, Lamar was absolutely correct. You're going to rewrite the sine squared, or no, was it Eli or was it Lamar? I can't remember. It's Eli. Rewrite it as 1 minus cosine squared. 1 minus cosine squared of x divided by cosine of x. All right, and that's just a Pythagorean identity. And then what? Algebra. We're going to divide the cosine into each thing. So we can't cancel a term with a factor. We have to distribute the division. So this becomes 1 over cosine minus cosine of x. We're looking good. We needed a cosine. We've got a cosine. Last thing, 1 over cosine is secant. And we get what we wanted, secant of x minus cosine of x. Boom. Super cool. So this is a seriously really good way to impress a girl on a date. I guarantee it. Did it with my wife, and now I'm married, right? So, and every student that's tried it has done it, has gotten a date. I haven't had any students do it, but 100% success rate. So,
Do you think wife was math teachers or?
no, nothing like that. Had nothing to do with the fact that I'm super hilarious as a person, right? I'm also super humble. No, I'm kidding. But try it this weekend. Let me know. Try during the break. Go on a date. Show work on through an identity problem for them. Super impress them, and we'll see what happens. Okay. I actually want to add something in here that is an important detail that we don't have enough space for it. I need to edit this document, but I want to take a side note on conjugates. Does anybody remember what a conjugate is? Yes.
It brings to, it's like if you have
Two terms.
and it's plus the other one, then it's minus the other.
Exactly right. So the conjugate of binomial of a plus b is A minus B and vice versa. Conjugates are actually super useful in mathematics. You will use them over and over again. If you're planning on taking calculus, you will definitely use conjugates at least once, especially in the limit section. You will definitely use it in the limit section, and then also in the derivatives section, the definition of the derivatives. So this is not something that's just going to be a one-off thing that never happens. It always happens. The key thing, why they're awesome, is that if you take two conjugates and you multiply them together, it always becomes a difference of squares. When you multiply conjugates together, you always get a difference of squares. And so that's why when I teach complex analysis, when I teach complex numbers, conjugates are very, very important with complex numbers. You don't need to write this down. But so do you guys remember what I is? The imaginary number square root 1, right? Square root of negative 1, excuse me. So when you multiply these things out, these are conjugates. And so what you end up with is you get a squared minus b squared I squared. And so if there's anybody of the faint of heart, if anybody's faint of heart, I need you to take a second because shit's about to get real. Boom! That's a hilarious joke right there. It went from a complex number to a real number. Things got real. Please don't tell my boss I said the S. But that's a hilarious joke. I love making that joke every time I can.
Oh,
It is on the recording. I'll mute it. You can do that on Apple Movie, right? iMovie, you can do that. You can add a little bleep in it. I don't know how to use Apple Movie. I'll figure it out. But either way, so that's a hilarious joke. But the point is, for us, the key thing is that they become a difference of squares. With complex numbers, it becomes a sum of squares because you get I squared, which becomes -1. So the minus cancels out. But for us, conjugates will always result in a difference of squares. Point being is now that you know this, you never have to FOIL this out. You just know that it's going to be the first term squared minus the second term squared. Whenever you have a conjugation, multiplying by conjugates, it always results in a difference of squares. So when it comes, like, that's really, really useful. Oh, go ahead.
like multiple, let's say one of them has two terms, like two A and B, and then the other one is A plus B plus C, what about that?
Then it's not going to be a conjugation, so it won't really, it'll be a distribution property. It'll be something completely different. But a valid point, you can act like there's actually a thing for that in mathematics. Like if you have x plus y times x minus y plus 1, you can think of that as this. And so when you take this and distribute it in, you know you have a difference of squares there, and then you just have to do it again there. So that is something you can do, but that's a niche situation. I only started doing that. I only started needing that in algebra.
You have to do one at a time, which does take time, but I'm able to like figure out myself.
Mhm.
Like, it's just, you know, the other teachers do it, like, they know, just by looking at it, they know what it's gonna be.
Mhm.
at the end, so it's just different.
It's the reason why we factor this so much in Math 126 and 181 and so on and so forth, that you start to notice the pattern. But if you don't notice it, you can FOIL out. There's nothing wrong doing that. But the key thing is that this is a nice tool in your toolkit. So math tool for toolkit, multiplying by conjugates. There are several rules that mathematicians always have on hand. If you've ever, I mean, like if you ever have, like you all should have your own little toolkit box. If you don't have a toolkit box, buy one. It's important. It's super useful to have. You always need a hammer. You always need a screwdriver. You always need a clamp at some point in your life. You always need a tape measure. Conjugation is probably the tape measure. It's useful in a few situations. And when you need it, you need it. But there are many different tools. Cleverly multiplying by 1, right? multiplying by 5/5 to get a common denominator, or multiplying by x plus 5 over x plus 5. That's cleverly multiplying y by 1. That's another math tool. Cleverly adding 0, right? Adding a number and then immediately subtracting it, another thing that we do. So all those things are very useful tricks, and this is another one of them. So sine over 1 plus cosine is equal to cosecant x minus cotangent x. You can start with either side. One would argue that the left-hand side seems more complicated, so we can start with that, but we can also prove it the other way if we have time. Like, I think we will have time. So in fact, I'm going to break this down. If we have time at the end, I'll prove it the other way too. But we got sine of x over 1 plus cosine of x. So I see a 1 plus a cosine of x, and that's close, but that's not an identity because it's not a cosine squared. But I know about my conjugation. If I decide to multiply this by 1 minus cosine of x times 1 minus over 1 minus cosine of x, like that, I'm not doing anything illegal. I'm cleverly multiplying by 1. That will not change the equation at all. So it now becomes sine of x minus sine of x cosine of x, all divided by 1 minus cosine squared of x. Take a second to digest that. Ask a question if you have it. Try and deduce it yourself. Try and see where I came from. The answer being that in the numerator, I distributed the sign in. That's why I got sine x and then minus sine x cosine x. And then you're multiplying by conjugation right there. So I'm multiplying by the thing that just changes the sign in the middle. So this will always result in a difference of squares. It'll result in 1 squared minus cosine squared. And that is sine squared. So this equals sine of x minus sine of x cosine of x, all divided by sine squared of x. At which point, what should I do? Take a second, don't answer out loud. Jake, I'll let you answer in just a moment, but I want to give everyone a chance to think what they think they should do. What's the worst thing that happens? You don't get the right answer. Are you going to die? No. So just try it. So Jake, what were you going to suggest?
Split it up and divide both halves of the binomial on top by this sine squared.
Exactly right. You're going to distribute the division. You're going to divide sine by sine squared and sine x cosine x over sine squared of x. You're going to divide each one by sine squared. So, or you could just factor out the sine of x and cancel it that way. You could do that too, but I'd like to do it this way. So I'm going to write this as 1 over sine of x minus cosine of x over sine of x. Take a second. Make sure you agree with me there. Make sure you agree with my algebra. You could write out that middle step of saying it's going to be sine of x over sine squared of x minus sine x cosine of x over sine squared of x. That's fine, but you don't have to. We all okay, that one. It's okay if we're not. And then we can use our identities. We know that 1 over sine is cosecant. Every s gets a c, so that's cosecant of x. And then cosine over sine is cotangent. And that's exactly what we wanted. We wanted to get to the right-hand side, which was cosecant x minus cotangent of x. So that's something we can do. All right. Yes, Brian.
We distribute the division from the sine squared of x to the numerator.
Mm-hmm.
I have got lost because I have sine of x over sine squared of x.
Mm-hmm. So there's an in-between step that I did not write, which this becomes sine of x over sine squared of x minus sine of x cosine of x over sine squared of x.
I just don't know how to get to that.
Sure. So remember, so this is a good point, and this is something that we need to become comfortable with in our mathematical career. So I'm glad you brought this up, is that cosine of x is just, and sine of x, any of these trigonometric functions, they're just a quantity. So if you have x over x squared, what does that become? 1 over x. One of the x's cancels and it goes away. Same thing, like the trigonometric functions are no different. In fact, if I have box over box squared, that becomes 1 over the box, and so on and so forth. So we need to get comfortable realizing that sine and cosine and tangent, they're just a box, and they can be canceled with other boxes. Okay? Great point. I'm glad you brought it up. This is another this is another thing that we'll also start to see when we get to trigonometric equations on why we need to do certain things. Okay, this one's a bit of a doozy. Because we could multiply by conjugates. So I'm going to think about this for a second. And I think the left-hand side looks more complicated, personally. So I'm going to think about so if I were to multiply by the conjugate of the denominator, if I were to do that, I would end up getting tangent squared of x minus cotangent squared of x, right? I'd end up getting that. Is that a Pythagorean identity? Is there anything that relates tangent and cotangent together? No. So that tool isn't going to be useful. So I was trying to hammer in a nail and I brought out the tape measure. I didn't need it. I already have like a nice little hole mentioned where I'm going to have that spot. So I don't need my tape measure. So conjugation is not going to be helpful here. Maybe it will, but I doubt it. There might be some weird things that we can do. So I'm going to write this. I'm going to rewrite our left-hand side. So tangent of x minus cotangent of x all divided by tangent of x plus cotangent of x. And remember, they cannot cancel because they're terms. You can't cancel terms vertically. You can only cancel factors vertically. So when all else fails, what do we do? If nothing else is getting us where we want to go, sines and cosines, always a good option. It's going to look more complicated, but that's okay. It's just a big Lego pile that we're working with, and we're just trying to find the pieces that we want. We need to find that 2x3 piece, and it's upside down, so we need to just find it. I don't think these Lego jokes are hitting, are they? No, they're missing. That's okay. But tangent is sine over cosine. Sine of x over cosine of x. Cotangent is cosine of x over sine of x. All divided by tangent of x, which is sine of x cosine of x. And then plus cosine of x over sine of x. Okay. Now what? Throw out a crazy idea. It would be ridiculous to do. I got fractions. When I think fractions and I need to add them together, what do you do? Common denominators. So it looks complicated, but let's just keep going with it. Trust the process and say, if whenever I have fractions, I want to get common denominators. So this is a complex fraction because it has fractions within fractions. If you go to my algebra review page, I talk about 2 methods to simplify complex fractions. There's a quick way, but it requires being a little bit clever. But there's the brute force way, which is what we mostly know. If you want to look up the faster way, just go ahead and look at the algebra review on complex fractions. But either way, I'm going to multiply this one by sine of x over cosine of x. And I'm going to multiply this one by cosine of x over cosine of x. And then I'm going to do the same thing in the denominator. I'm going to multiply this by sine of x over sine of x. And this by cosine of x over cosine of x. Doesn't look pretty, but it's okay. I mean, beauty's in the eye of the beholder. Maybe they think it's pretty. Maybe math thinks it's pretty. So in the numerator, I've ensured that the denominator of the big numerator, what should the big, it should be sine theta or sine x cosine x. Same thing with the denominator. So this will now be, if we're comfortable with our algebra skills, this should be sine squared of x minus cosine squared of x, all divided by sine of x cosine of x. And then the big bar, the main bar in town, which wherever you go for that. And then it'll be sine squared of x plus cosine squared of x, all divided by sine of x cosine of x. Getting better, getting better. I'm noticing something nice. The denominators are going to cancel. You can either write it out and flip and multiply, or you can realize right now that they're going to cancel. It's your call. I'm going to show that nitty-gritty detail, but it's your call. This then becomes sine squared of x minus cosine squared of x, all divided by sine of x cosine of x, times the reciprocal, because when you divide by a fraction, you flip and multiply. So it's times sine of x cosine of x, all divided by 1. I'm gonna actually do one more step. I'm gonna do 2 steps at once. I probably shouldn't do that. I probably should write it down in multiple steps, but I'm gonna do it that way. You can you can even make a mention of it. You can mention that this is 1. You can do that either way. The sines and cosines in the numerator and denominator cancel. And all I'm left with is sine squared x minus cosine squared x. Okay, that's good news. So try and take your little victories as you take them. We got rid of fractions. We no longer have fractions, which means we're closer than we were before because we need to get to no fractions. What else can I do now? I'll look for a Pythagorean identity for cosine. Yes. So I looked at this right here and saw, oh no, it's a minus sign. That's not going to be a Pythagorean identity. But I know that I can rewrite sine squareds and cosine squareds in terms of the other function they're dealing with. So this right here, this is 1 minus sine squared of x. And so the minus sign will get distributed in. You'll get -1 plus sine squared, which gets us to our final answer of 2 sine squared of x minus 1, which is exactly what we wanted. Okay. Now we need a Cliff Bar. Just a little nap. I always usually speaking, unless you're very confident on where you're going, which you get to that point. I know I've gotten to this point where I trust myself enough to just follow my nose, as Toucan Sam always suggests, to the flavors of different fruits wherever they grow. And I will just go through with the pink, purple, orange, and green. But if you're uncertain, just use some scratch paper. Start it off. If it doesn't work, cross it out in the scratch paper, start again. Right.
Those fractions with fractions.
From here to here? From here?
Yeah.
Yes.
That's where I got.
Okay. Thank you for letting me know. In the future, please, if you're lost at any step, just interrupt me if I haven't asked for things. I appreciate you letting me know. So the denominators here, one way to think about it is if it is freaking you out to have like the sines and cosines in the denominator, look at it purely in terms of like the like new things. Write it as like if you had 1 over x minus 1 over y, what would be the common denominator?
What?
xy. So what do I need to multiply this by to get xy? Y over y. What do I need to multiply the other one by? X over x. So in the same idea, the common denominator for sine and cosine would be sine cosine, sine x, cosine x. So what is this missing? It's, I don't know. Oh, that's weird. That's weird. That should not be a cosine. Thank you. Everything else was fine. I don't know why I wrote that. I was going off on a tangent. Yeah, that's a hilarious one. I should make that joke more often. That's a good one. But yes, is that okay? Is that cleared up? Okay, perfect. Thank you for catching that. Thank you. Okay. Oh, yes, Marcus.
You did sine squared of x minus 1 minus sine squared of x.
Mhm.
So you end up adding the signs together to get a positive 2 signs.
Yes, because the minus, oh, so this is one thing you could draw. Let's use red. The minus sign will get distributed. So the minus sine squared x will now become a plus sine squared x. And the positive one will now become a minus one. Please ask, like, I'm glad you guys are asking these excellent algebra questions. Algebra is key, and sometimes we need a refresher on things. Okay. Next thing, did anybody go over even and odd in their 126 classes? I'm curious. Because I don't teach it anymore. It's not important. It's an interesting property. A function is odd if it is symmetric with respect to the origin, which makes it so that if you plug in a negative x into the function, you get the negative sign comes right out front. So that what that's saying is that when you change the x coordinate from the right to the left, the y coordinate goes from the top to the bottom. That's what it means. And an even function is one that is symmetric with respect to the y-axis. So if you plug in the negative version of your x component, if you flip it over to the other side, it gives you the same y value. So f of negative x is equal to f of x. So there's a lot of cool properties about even and odd. It's a fun thing to do, I guess, but it's not really super useful in the long run. But it is interesting for trig functions because sine and tangent and their soulmates, cosecant and cotangent, those are all odd functions. So that is to say, sine of negative x is equal to negative sine of x. Tangent of negative x is equal to negative tangent of x. Cosecant of negative x is equal to negative cosecant of x. Cotangent of negative x is equal to negative cotangent of x. And then even ones are secant and cosine, particularly cosine. Cosine is an even function, which therefore means that secant must be an even function as well. Useful little properties, not super important, but they do pop up from time to time. I'll provide those. Those are ones that don't really aren't intuitive. So I will provide those on the exam. You don't have to have the odd trig function and even trig functions memorized. But if we use those properties, so I mean, yes, we can do sine cosine of negative 60 degrees. We can go backwards down 60 degrees and figure out what cosine will be. But why do that when we can use these even and odd properties? That's super cool. So this is equal to just cosine of 60 degrees because cosine is an even function. The negative sign doesn't really matter with an even function. And cosine of 60 degrees, that's the big angle, which means that the vertical side length is the big side length, and the bottom one, which will be cosine, is the smaller one, which is 1/2. So it'll be 1/2. Cosecant of negative 225 degrees. Cosecant is the soulmate of sine. Sine is odd, and therefore so is cosecant. So this is equal to negative cosecant of 225 degrees. And so that will be an interesting situation. So 225 degrees is right there. Cosecant is going to be 1 over cosine, or sorry, 1 over sine. So it's going to be 1 over negative square root 2 over 2. So this will be negative 1 over negative square root 2 over 2, which is, I mean, you can rewrite it as 2 over square root 2, which is just square root 2. I'd be fine with you just leaving it as 1 over square root 2 over 2 or just 2 over square root 2. Either any of those options is fine. It's good algebra practice, but not necessary. So just so we're clear, I found to figure this out, I knew that cosecant was 1 over sine. Sine of 225 degrees is negative square root 2 over 2. So this is 1 over negative square root 2 over 2. The negatives cancel. That's why it's now positive. And then I'm going to flip and multiply by the fraction in the denominator. That's why it's 2 over square root 2. But then you can also simplify that by canceling out a square root 2. Because 2 is square root 2 squared. A lot of silly algebra going on there. Tangent of negative 7 pi over 4. Tangent is an odd function, as you see up above, but you can memorize it if you get there. So this will equal, come on, negative tangent of 7 pi over 4. 7 pi over 4 is 1 less than 2 pi. So we're in the fourth quadrant, but you can also look at this unit circle. 7 pi over 4 is there. Tangent is y over x. So it's just going to be negative 1. So this is equal to negative 1, which is positive 1. And last but not least, secant of negative 11 pi over 6. That's secant, and secant is an even function because cosine is an even function. So this is just equal to secant of 11 pi over 6, which you can either use the unit circle that's provided, or you can utilize your knowledge of the radians to know that that's a little less than that's 1 less than 2 pi. So that's going to go all the way around to right there. And we're talking about secant, which is 1 over cosine. So I'll even write that down. This is equal to 1 over cosine of 11 pi over 6. And cosine of 11 pi over 6, that's the x coordinate, that's square root 3 over 2. So this is 1 over the square root of 3 over 2, which you could leave it like that or write it as 2 over square root 3, or you could write it as 2 square root 3 over 3. However you want to write it is fine with me. I'd be fine with just that. All right. So now the reason why we bring that up is now we get an extra thing to throw into the mix in terms of proving identities. So on the identity page for your upcoming exam in 4 weeks time, I think it's 4 weeks time, there's going to be that sheet that has you deduce them. And then at the top, I'll also write the even and odd stuff so that you don't have to have that memorized. All right. So now that we know what even and odd trig functions are, we can, well, I mean, know what they are. We will just use this knowledge. We're going to prove the identities using even and odd features and then everything else. Okay. So I would always recommend getting rid of the negative x's. Write it all in terms of x's if you can. So I'm going to start with the left-hand side. That seems far more complicated to me. Negative sine of x looks pretty nice. So this then becomes, so 1 plus sine of negative x over 1 plus cosecant of negative x. Sine is an odd function, so I can bring the minus sign out front. So that's going to be 1 minus sine of x, of positive x now. And cosecant, which is sine soulmate, it's also odd. So this will be 1 minus cosecant of x. And so that's from even odd. way. And there's no one right way. You could always resort to using sines and cosines. That might be a good option. If I were to multiply, do you think multiplying by conjugates might help? It might. Worth a shot? No? You're certain? Certain that it won't help. Because if it, oh, that's a good point. Let's see. If I were to multiply by the conjugate of this, that would be 1 plus cosecant of x. So don't write this down. This is just me theorizing. Then if I FOIL that out, it's going to be the difference of squares. It's going to be 1 minus cosecant squared of x. Is that a trigonometric identity? 1 minus cosecant squared of x. It is and isn't at the same time. It's negative cotangent squared. But so you could use it, but maybe it's just nice to use sines and cosines. How about that? I don't know if it's going to work out. I truly don't. I'm guessing. So I'm going to rewrite cosecant in terms of sines and see if I see a sign from above. So this will be 1 minus sine of x over, oh, wait. I didn't mean to erase all of that. I didn't mean to re-erase the even odd. So I'll rewrite this as 1 minus sine of x over 1 minus 1 over sine of x. Okay. I see a fraction. Whenever I see fractions, I want to try and combine them. I think that's a good guess. Maybe it works, maybe it doesn't. I'm getting closer to that flavor of fruit wherever it grows. So I'm going to multiply the 1 by sine of x over sine of x, all squished up like that. And that would just be algebra. It's just algebra because I'm just multiplying by 1. I'm not doing anything crazy. And so that'll equal 1 minus sine of x, all divided by sine of x minus 1 over sine of x. Which then by algebra, you're dividing by a fraction. I'll let you write that down first. And please ask a question if you have it. This is weird. They're always weird. That's part of their charm. Common denominators, always a good option. Maybe it works, maybe it doesn't. But so multiply by sine of x over sine of x is that 1. Now you have a common denominator in the big denominator. So it becomes sine of x minus 1 over sine of x. You're dividing by a fraction, so you can flip and multiply. This then becomes 1 minus sine of x times sine of x divided by sine of x minus 1. Okay. Not looking great, at least at first glance. But I look at that 1 minus sine and then sine minus 1. Those are very similar. You can factor out a negative 1. That's always a good, like sometimes you might need to factor out a negative 1. And if you do that, if I factor out a negative 1, I get 1 minus sine of x now. The sign now becomes negative and the 1 now becomes positive. And so I just decided to rewrite it. But it's fine to leave it as is. You'll notice that eventually it will cancel out. And so the algebra cancels these out. And we just get negative sine over negative 1, which is just negative sine. The negative 1 will stick around. So, Brian. Sure. Let me go ahead and put an asterisk here. So the reason, excellent question. So sine of x minus 1. If I factor out a negative 1, I'm allowed to do that. That's always an option. And then it'll become negative sine of x plus 1. And then by the commutativity of addition, I can flip-flop the numbers, right? 5 plus 3 is the same thing as 3 plus 5. So I can swap them. And this becomes negative, and then it's going to be 1 plus negative sine of x, which then becomes -1, negative quantity 1 minus sine of x. I can change the adding a negative to subtraction. Is that okay? Weird algebra, but now you know it. Now you've seen it. You accidentally punched a hole in your wall while listening to Rage Against the Machine, and now you have to fix a hole in your wall. Now you know how to fix a hole in your wall. Not speaking from personal experience. I was an angry kid. Any other questions on this one? So we get to put a cool check mark. Last one. Always change the negative x's into positive ones by using the even and odd properties. If you can get everything into the same variable, that's the key. So secant is 1 over cosine. Cosine is even. So this becomes secant of x. This is negative sine of x, and this is negative tangent of x. So the double negatives cancel out. And so it's still just minus. There's 3 negatives total. So it becomes secant x minus sine x cosine x, or sine x tangent x. And we're hoping that's going to equal cosine of x. Oh, no. I'm getting ahead of myself. Just working with the left-hand side. The left-hand side looked far more complicated. The stuff you have to break down, the more options you have. You go down a lot more avenues to try. All right. And from there, what should I do? What's your thought? Over rewrite everything in terms of sines and cosines. Beautiful. Beautiful. So this is going to be 1 over cosine of x minus sine squared of x over cosine of x. Make sure you agree. Oh, yes. Aaron. It would become a positive sine of x tangent of negative x, and then the extra negative here. There's 3 negatives. And so they all just can't, like, they 3 negatives results in a net negative. Right. Good?
Yeah.
Sure? Okay. And then they have the same denominators, so we can combine them. This equals 1 minus sine squared of x over cosine of x. But we know what 1 minus cosine squared of x is, or what 1 minus sine squared of x is. That's cosine squared. So this is cosine squared of x over cosine of x. One of the cosine x's cancels with one of them up top, and we're just left with cosine of x, which is exactly what we wanted. Any other questions on that? So seriously, treat it like a Lego, and I think you'll have a much better time. Realize that it's a game. It's just all about using the 3 rules of the game, like the 3 different types of rules for the game, and trying to get to the very, very end by using your Legos. All right. That'll do it for today. Don't worry, I'm coming right back to this, but I told you guys that there was going to be another option for this one. If you start with this one, if you start with the right-hand side, so cosecant is 1 over sine, cotangent is cosine over sine. You can combine them, and you should be able to work with that. So try that at some point this weekend. Otherwise, if you have any questions, feel free to email me. The last page of the notes is all the identities you need. So you can bust that out when you're doing your homework so you don't have to keep looking them back up. If you have any questions, email me. Otherwise, you guys have a great rest of your day, a great weekend, and a great spring break. Spend time with the family and friends that you are around. Social media isn't real. It's causing a major depression epidemic in our children. So maybe we shouldn't allow it. Maybe it should be regulated. Maybe talk to your senators and your congresspeople about that. Maybe we can get some change going. That's a good idea. It's a really good idea. Please do it for all of us, and have a great spring break.